Exercise 70. Here an element x is given in some group whose order is n. N is some positive integer. And r and s are some integers. We have to find a necessary and sufficient condition such that the cyclic group generated by x to the power r is contained in the cyclic group generated by x to the power s. So we will first assume this and then we will see what condition we end up with. Solution. We first assume that this inclusion is true. Then x to the power r belongs to the cyclic subgroup generated by x to the power s, because this belongs to this group, so it also belongs to this, and hence so this element belonging to this group means what? This will be an integral power of x to the power s there exists an integer k such that x to the power r is equal to this. Hence, x to the power r equal to x to the power sk using the rules of exponents, or x to the power r minus sk equal to identity. This implies if x to the power r minus sk is identity, where clearly r minus sk is an integer, so the order of x will divide this exponent. So this implies n divides r minus sk, that is nl is equal to r minus sk for some integer l. So now what are we getting? R is equal to nl plus sk. Now note that nl plus sk is a linear combination of n and s, and the coefficients l and k of course are integers, and we know from properties of the greatest common divisor of two integers that this linear combination is divisible by the greatest common divisor. Since GCD of n and s divides nl plus sk, we have this divides r. Okay, so this divisibility relation becomes a necessary condition for this to be true. Necessary in the sense that if this happens, then this should necessarily happen. This is a consequence of this, or in other words, this implies this. Okay, we will now show that this is also a sufficient condition, that when this happens, it's sufficient for this to happen. That is, in that case, this will also be true. Conversely, assume that the greatest common divisor of n and s divides R. Note one more thing, that because n is the order of some element, n is by definition a positive integer. Okay, so there is no question of having 0 n, and that is why, because n is a non-zero integer, actually we do not in fact need positivity of n, but we only need its non-zeroness. So yes, whether it is 0 or not, that does not matter. One of these two integers is non-zero. That is enough for us to have the fact that GCD of n and s exists, first of all. If both n and s were 0, then of course GCD does not exist. Okay, so that problem is not there. Now we are conversely assuming this condition. We will prove that this is contained in this. So essentially the argument is just like this one in the reverse order. Then R is equal to, say, I times GCD of n and s for some integer I. But we know that the greatest common divisor itself is a linear combination of the two numbers n and s. We know that this is equal to, say, alpha n plus beta s, where these are some integers. Now look at this calculation. X to the power r becomes x to the power I times GCD of n and s. So this is I times alpha n plus beta s. Now using the rules of exponents, we can write this power as x to the power n whole to the power I alpha times x to the power s whole to the power I beta. Because order of x is given to be n, so this will become identity. So we ultimately get this. since I and beta are both integers, so I beta is some integer. So that means we have expressed x to the power r as an integral power of x to the power s, and hence this definitely belongs to the cyclic subgroup generated by this, and that's why x to the power r belongs to this. But since this is a group, so if x to the power r is an element in this, then the cyclic subgroup generated by x to the power r, this one, will be contained in this group by closure property. So thus this is contained in this cyclic subgroup. So this divisibility relation is a necessary and sufficient condition for this inclusion. And before we wrap things up, before we clean it, let's once more see what this is. The subgroup that is contained in the other one, for this one we have R, and for that one we have S. For the bigger one we have S. GCD of that S and N should divide the exponent of the smaller one. Okay. (71). Suppose A is a group element such that the order of a to the power 28 is 10 and the order of a to the power 22 is 20. Determine the order of A. Okay. Let the order of A be denoted by n. Now, since these conditions are given, what do these things mean? First of all, order of a to the power 28 is 10 means the 10th power of a to the power 28 is the identity and no smaller power is the identity. So we will use that first portion, that is a to the power 28 whole to the power 10 is identity, and the same thing for this one. So a to the power 280 this is equal to identity, and similarly a to the power 440 this is also equal to identity. But then because these powers these exponents give us identity, so the order of a will divide these exponents. So n divides both 280 and 440. Hence, n divides their greatest common divisor also by property of GCD. GCD of 280 and 440, and this GCD turns out to be 40. Okay, thus so n should divide 40. N should be a positive divisor of 40. Positive because order can never be 0 or negative. So n belongs to the set of all positive divisors of 40, which we can find. These are the positive divisors of 40. 140, 220, 3 is not an option, 4, 10, and 5, 8. Do we have anything else? 6 does not divide 40, 7 does not divide 40, and once we hit 8, we are going to get these things back. Okay, now from among these possibilities, we have to rule out the ones that actually do not occur. But how? For that, okay, first of all, because a to the power 28 has order 10, so that means a to the power 28 itself cannot be the identity element. That is, we should not have this. Now this condition arises from several possibilities. For example, if a is identity, then this can happen. If a square is identity, then also this can happen. If a to the power 4 is identity, then also this can happen. And we don't want this to happen, so that means none of these three possibilities is true. And as such, n cannot be 1 or 2 or 4. So these things are automatically ruled out. But we have to write the reason. Since this is equal to 10, we must have a to the power 28 not equal to identity. Then a is not identity, a square is not identity, a to the power 4 is not identity, and some other powers are also not identity. For example, a to the power 7 is not identity, then a to the power 14 is not identity, but we don't need those powers because we don't have the corresponding exponents here. Hence, n is not equal to 1, n is not equal to 2, and n is not equal to 4. Okay, so we have ruled out 1, 2, 4. Okay, what about 5? Can n be equal to 5? Actually, n cannot be equal to 20 or 10 or 5 or 8. 40 is the only possibility. Okay, so now instead of looking at equations or inequalities like this, we try something else. Recall that we already know how to calculate the order of the power of an element when we know the order of the element. Now if we apply that here, then according to that formula which calculates the order of a to the power 28 in terms of the order of a, the left hand side of this equation will be the order of a, which is n, divided by the greatest common divisor of n and 28. Okay, this should be equal to 10. Now this GCD of this should be equal to 10. So what does it mean? It means that n cannot be 5, of course, and n cannot be 8 also. Why? Because if n is 5 or 8, then whatever the denominator is, since we are dividing by the denominator, this can never be equal to 10 because already 8 and 5 are less than 10. Okay, so 8 and 5 will be ruled out like that. Also, equal to order of a to the power, sorry, it's not 20, yeah, it's 28. The other one is 22, equal to n divided by GCD of 28 comma n. So that means this shows that n can, instead of writing these things, we could have used this itself. What is the point of writing this part then separately? At once we can rule out many of the things. Note that equal to order of a to the power 28 equal to n divided by GCD of n and 28. This implies that n is not equal to, no number smaller than 10 is a possibility here. So 1, 2, 4, 5 and 8, all of them are rolled out at once. N is not equal to 1, N is not equal to 2, N is not equal to 4, N is not equal to 5 and N is not equal to 8. Okay, now next we have to rule out 10 and 10 and 20. Also, the other equation is this: 20 equal to order of a to the power 22, n divided by GCD of n and 22. So here values smaller than 20 cannot be taken in place of n. So that means 10 is ruled out. Actually, using this itself we could have done this part also, but anyway, thus n is not equal to 10. Okay, so now we are left with two possibilities, 20 and 40, out of which we have to show that 20 actually is not a possibility. If n is equal to 20, then this equation itself will give us a contradiction. Then 20 is equal to 20 divided by GCD of 20, 22. This greatest common divisor is 2, because 2 is the largest. You can just simply calculate it and you will see that the GCD is 2. This one is divisible by 5 and 4. 5 does not divide this. 4 itself does not divide this, but 2 divides this. So this is 2. This is equal to 10. Thus, n is not equal to 20. So we must have order of A equal to n equal to 40. And you can see that when you have n equal to 40, then these equations turn out to be true, which you can see from here. If you take n equal to 40, say this here, then 40 divided by GCD of 40 and 28. Seven does not divide 40. 4 divides 40. So this is 4. This is equal to 10. So you see 10 equal to this. Now what about that other one? 40 divided by GCD of 40, 22. 11 does not divide 40, so the GCD is 2. So this is equal to 20. So 40 is actually a possibility. In fact, we should write that also. Note that in this case order of a to the power 28 is 10 and order of a to the power 22 is 20. So the solution ends here. Then 72. Let A be a group element such that order of A, so here now the order of the element itself is given, it is 48 for each part. For each part, find a divisor k of 48 such that the cyclic subgroup generated by a to the power 21 equals the one generated by a to the power k. Then b a to the power 14 c and here we can of course use that necessary and sufficient condition we found in exercise 70. By the solution of exercise 70 above, we get what? You see, we want both these inclusions to be true, this as well as this. So according to our necessary and sufficient condition for this inclusion to be true, an equivalent condition is this: GCD of the order of A, which is 48, and K should divide 21. And for this one to be true, an equivalent condition is this: GCD of 48 and 21 should divide K. Well, I'm using this notation. I'm not sure whether the author has used it. This vertical bar means the integer on the left side divides the one on the right side. Okay, it is just, we simply read it like this: GCD of 48 and K divides 21, or in other words, 21 is divisible by the GCD of 48 and K. That's what it means. Okay, so from these two divisibility relations, we will be able to figure out one possible K. So we get GCD of 48 and 21 dividing K, and 48 and K dividing 21. Since 48 and 21 is divisible by 7, but 7 does not divide 48. 21 is divisible by 3, and 48 is also divisible by 3. So in this case, the GCD is 3. We can take K equal to 3. Okay, so if we are taking K equal to 3, then the first divisibility relation is of course true, because 3 divides 3. What about this one? GCD of 48 and 3 is 3, and 3 definitely divides 21. So both those inclusions are true, which proves that these two cyclic subgroups are equal. B, the other parts are similar. For what is the exponent? 14. We need GCD of 48. Order of A stays the same. It's 48. It's given, that is fixed. We need this GCD to divide K, and we need this GCD to divide 14. This one again, 7 does not divide 48, so this GCD is 2. So there it was 3, here it's 2. So we can take K equal to 2. Then in part C, the number is 18. And oh, by the way, when k is 2, then here in the second divisibility relation, the GCD is 2 and 2 definitely divides 14. So our choice k equal to 2 is okay. This divides 18. Okay. 6. 3 divides 48. 2 also divides 48, but 9 does not divide 48. So this GCD is 6. In this case, we can take k equal to 6. And if we do that, then here the second GCD will be 6 and 6 divides 18. So this completes the solution. Then 73. Let P be a prime. Show that in a cyclic group of order p to the power n minus 1, where n is some positive integer. Every element in such a group is a pth power. That is, every element can be written in the form a to the power p for some element a in the group. This a, of course, is not fixed. It will depend on the element that you are trying to express as a pth power. That this a will change likely. Okay, so now P is given to be a prime and our cyclic group is given to have this order. And the original group that is given is itself cyclic. That should also be noted. Let A be a so it will have some generator. So let A be a generator of the group. Since the greatest common divisor of P and P to the power n minus 1 is 1, which is easy to see. The only two positive divisors of P are 1 and P, because P is a prime. Out of them, P does not divide this one. So the only positive common divisor of P and P to the power n minus 1 is 1. So that is also the greatest one. So if this happens, then the third corollary to theorem 4, am I getting the numbers correct? Let me see. Third corollary to theorem 4.2 implies that this element A is a generator, but now a to the power p is also a generator. Okay. We now have to prove that every element is some pth power. Now let B be any element in the cyclic group. Now because a to the power p is generator, B will be some power of a to the power p. Then there exists some integer k such that p is equal to this. But then by using the rules of exponents, b is also equal to this, because a to the power k after all is again an element in the cyclic group. So we have expressed b as the pth power of a to the power k. So that's why every element in the cyclic group is a pth power. So here the solution ends. 74. Prove that H equal to the set of these 2 by 2 matrices where n is any integer is a cyclic subgroup of the general linear group of invertible 2 by 2 real matrices under, of course, matrix multiplication. Note that this matrix belongs to H because 1 is an integer. So for n equal to 1 you get this matrix in H. We will now show that this in fact is a generator of this cyclic group. I mean, it is an element in H that generates H, and hence H will be cyclic. we claim that the nth power of this matrix is nothing but this. For all integer n. We will now prove this claim by induction on n for non-negative values of n. We first prove this claim for non-negative integers n by induction. The case n equal to 0 is trivially true. Oh, no. I think what I have claimed here is not entirely. Is it true when n is equal to 0? When n is 0, by the definition of integral powers, this is the identity element in this group, which is the identity matrix. Yes, in that case we will have 0 here, that means 1 0 0 1, and when n is 0 the right hand side is also 1 0 0 1. Yes, it is true, it is trivially true. Now assume that it's true for some non-negative integer n. Then what about this? N plus 1, 1 1 0 1, n 1 1 0 1. This, by our induction hypothesis, is equal to 1 n 0 1, and this one is 1 1 0 1. We now perform the multiplication. 1 1 1 plus n 0 0, that means 1. 1 plus n, that is n plus 1. 0 plus 0 0, 0 plus 1 1. So that's it. Here we have n plus 1, here the exponent is also n plus 1. This completes the induction. Okay. Next, let n be a negative integer. Then minus n is a positive integer, and hence, by what we have already proved here, minus n equal to this. This implies this to the power n equal to 1101 to the power minus n inverse. Okay, minus nth power is the one that we have inside, and whole inverse or to the power minus 1, same thing. So this is 1 minus this inverse of this matrix, and one can see that this inverse is nothing but 1n01. If you are doubtful of this, then you multiply these two matrices. One plus 0, 1, n minus n, 0, 0 plus 0, 0, 0 plus 1, 1. So you get the identity matrix. You can switch the places of these matrices, change the order. That product will also be the identity matrix. So this actually is the inverse of this. So you see that even when n is negative, that same claim is true. Thus, so what does it mean? It means that the set H is such that every element in it is an integral power of this matrix 1101. So this matrix generates H, and hence H is a cyclic subgroup. Thus, all of those things we can say at once using this notation. H is the cyclic subgroup generated by this matrix. Then 75. Let A and B belong to a group. If the order of A is 12, the order of B is 22, and the cyclic subgroups generated by A and B do not intersect trivially. That is, their intersection is not the trivial group consisting of the identity. If these conditions are true, then what do we have then? Then prove that a to the power 6 is equal to b to the power 11. Okay, we shall use Theorem 4.3, that is the fundamental theorem of cyclic groups. Throughout this solution. So the different parts the theorem has, they will be used without any further explicit mention. Since this intersection is a subgroup of both the cyclic groups, so by that theorem, the order of this subgroup will divide the order of this one and also the order of this one. The order of this intersection divides this order, which is 12, and also the order of the other subgroup, which is 22. Hence, this divides the greatest common divisor of these two integers, 12 and 22, which is 2. So because 2 is prime, this order is then either 1 or 2. But it cannot be 1 because it's given that the intersection is not the trivial subgroup. Since we must have this order equal to 2. Okay, now this is a subgroup of this cyclic group. So by that theorem again, the intersection itself should be a cyclic group. Similarly, since this intersection is a subgroup of this cyclic group, it should be a cyclic subgroup of this group. So that means this intersection will be generated by some power of A, because it's a cyclic subgroup of this group. At the same time, it should be generated by some power of B, because it's a subgroup of this one also. And because the order of this group is 2, we know exactly which elements will generate it. Since this is a cyclic subgroup of both this and this, we have it should be generated by this power of A. Order of A is 12. 12 divided by 2, that is this, and like that the intersection will be generated by this power of B. Order of B is 22 divided by 2. This 2 is the order of the intersection. Okay, you go back to you go to the statement of this theorem. There you will see that every cyclic group of order n has exactly one subgroup of order k, where k is the positive divisor of n, and that subgroup itself is cyclic and it is generated by a to the power n by k. That thing we are using here. Hence, this will be b to the power 11, hence this is equal to b to the power 11, but why? That is because these two groups are equal, so a to the power 6 should belong to this group, but this group has exactly two elements. One of them is the identity and the other is b to the power 11. This, and that is because its order is 2. And a to the power 6 itself cannot be identity, because had that been the case, the order of this would have been 1, not 2. So the only possibility is that a to the power 6 must be equal to the other element, that is b to the power 11. That's how we are getting this. So this ends the solution. 76. If X is an element of a cyclic group, of order 15 and exactly two of these three elements, x cube, x to the power 5 and x to the power 9 are equal, then determine the order of x to the power 13. Okay, so the cyclic group has order 15 and x is an element of this cyclic group. X is not given to be a generator, okay, keep that in mind, such that out of these three elements exactly two are equal and the third is different. We don't know what they are. Under these given conditions we have to find the order of x to the power 13. So here the solution goes like this. We already know that in a cyclic group, in a finite cyclic group, the order of every element divides the order of the group, and that is also coming from this theorem 4.3. So we are directly writing since the order of x should divide, here I am again using that notation, okay, this divides 15. So what are the possibilities? Order of x can either be 1 or it can be 3 or it can be 5 or it can be 15. But order of x cannot be 1. Let's see why. If order of x is equal to 1, then the only possibility is that x has to be the identity, and in that case x cube, x to the power 5 and x to the power 9, all of them are equal and all of them are equal to the identity, which contradicts the hypothesis that exactly 2 of them are equal. So order of x cannot be 1. Okay, now since exactly 2 of these 3 elements are equal, we have exactly 2 are equal. We are not going to use this hypothesis fully, but we are going to use its part that 2 are equal. If those 2 equal elements are this, that is, if in the group x cube is equal to x to the power 5, then that implies x square is equal to identity, or if x to the power 5 is equal to x to the power 9, then x to the power 4 is equal to identity, or if these 2 are equal, then x to the power 6 is identity. Okay, so that means in our group one of these 3 equations must be true. Either x square is identity, or x to the power 4 is identity, or x to the power 6 is identity. If this is the case, then the order of x should divide 2. If this is the case, then the order of x should divide 4, and if this is the case, then order of x should divide 6. So that means the order of x cannot be 5 or 15, because 5 divides neither 2 nor 4 nor 6, and 15 of course also does not divide any of this, because 15 is in fact greater than them. Thus order of x is not 5 and order of x is not 15. So it is neither 1 nor 5 nor 15. So the only possibility is it is 3. Now we have determined the order of x. So we can now use the usual formula to calculate the order of x to the power 13. Thus, this order is equal to the order of x divided by the GCD of the order of x and 13. That is 3 divided by GCD of 3 and 13. This GCD is 1. So x to the power 13 also has order 3. And that's the solution. Then 77. Determine the number of cyclic subgroups of order 4 in the dihedral group Dn. So in the dihedral group Dn, how many cyclic subgroups of order 4 are there? We have to find that number. Now a dihedral group, you already know, has two types of elements. Each element is either a reflection or a rotation, and we also know that reflections are elements of order 2. So none of them can generate a cyclic subgroup of order 4. So if there is such a subgroup, it should be generated by a rotation. Since reflections in Dn are of order 2, a cyclic subgroup of Dn of order 4 must be generated by a rotation. And as such, it should be contained in the subgroup of all rotations. That means it should be a subgroup of the subgroup of all rotations, which itself is cyclic, and its generator is the rotation through an angle 360 divided by n. Now, if we have a cyclic subgroup of order 4, then that is a subgroup of this, which itself is cyclic. So we can use the results about cyclic groups here. Although the entire group Dn is not cyclic, but now our things have come down to cyclic groups. and by theorem 4.3 we know that this cyclic group has exactly one subgroup of order 4. Or a subgroup of this. Thus, okay, so when such a cyclic group of order 4 exists, then there can be only one, because it becomes a subgroup of this cyclic group, which by the fundamental theorem of cyclic groups can have only one subgroup of order 4. And when there is no such subgroup, then fine. One more thing, when will this happen? When shall the group have a cyclic subgroup of order 4? In that case, 4 should divide the order of this cyclic group, because it's the corresponding cyclic group of order 4 is a subgroup of this cyclic group. So by the fundamental theorem of cyclic groups, its order should divide the total order of the cyclic group, bigger cyclic group, which is n, because there are n rotations. So that's why Dn has exactly one cyclic subgroup of order 4 when 4 divides n and no cyclic subgroup of order 4 when 4 does not divide n. Okay, so either 1 or 0 depending on these situations. So that is the solution. Then (78) if n is odd, prove that Dn has no subgroup of order 4. If one has Lagrange's theorem, which we have not got yet, at one's disposal, then this exercise can be written in the solution can be written in only one line. But we don't have that, still we will solve it somehow. We have its version for cyclic groups, that is, every subgroup of a finite cyclic group is such that its order divides the order of the original group. That in general is true, that is Lagrange's theorem. Okay, so here we can write the solution like this. So we will suppose that Dn has see one more thing. In the previous exercise, we determined the number of cyclic subgroups of order 4. Here, however, we are saying that when n is odd, Dn has no subgroup of order 4, cyclic or non-cyclic, that does not matter. There is no subgroup of order 4. So suppose Dn has a subgroup H of order 4. since n is odd, n is odd means definitely 4 will not divide. Okay, this is looking like plus. 4 does not divide n. And hence by the previous solution. Previous solution means solution to the previous exercise. Okay, you should understand that. The previous solution implies that there is no cyclic subgroup of order 4 in Dn, but we have already supposed the existence of a subgroup H of order 4. That means H cannot be cyclic. H is not cyclic. Okay. Hence, H is not cyclic means what? H is not contained in the cyclic subgroup of order n in Dn, namely the group consisting of all the rotations and which is generated by this particular rotation, the smallest one, smallest non-trivial one. But why? Why does H not why is H not a subset of this cyclic group? That also comes from the fundamental theorem of cyclic groups, because we know that every subgroup of a cyclic group is cyclic. So if H is contained in this, H should be cyclic. However, we have concluded just now that H is not cyclic. So H cannot be entirely contained in that cyclic group of all rotations. Okay, so that means what? That means that H should have a reflection. Okay, all of its elements cannot be rotations. H must have a reflection. Now you can ask whether H can have only reflections. If H has only reflections, say, of course, because H is a subgroup after all, it should have the rotation R naught, R0, which is the identity. That is fine, but the others are the reflections. F1, F2, then because the order of H is 4, so we should have another one, F3. Now these are naturally distinct reflections, because that's why they are making the order of H equal to 4. Now if you have two distinct reflections, then their product is a rotation. These are things we have already seen, we saw before when we solved many exercises on dihedral group and its element structures. Now this is a rotation. Now can this rotation be R naught? If it is equal to R naught, in fact we proved this fact previously, but again we are demonstrating. If we are assuming this to be R naught, then multiplying on both sides from the right by the reflection F2, you get this. Now since every reflection has order 2, so this thing vanishes. and on the right side we have F2. This contradicts the distinctness of F1 and F2. So that means if F1 and F2 are different, distinct reflections, then their product is a rotation that is not equal to R0. But then we are getting a rotation which clearly it is none of these reflections, because rotations and reflections are different elements, okay. But then we don't have any place for this element in H. That is a contradiction. So H should have reflection as well as rotation. And we can, instead of writing all these things, we can simply mention this fact in short like this. Since okay, exactly what has been used here in concluding this fact? Okay, since that means it has we can write like this: since the product of two distinct reflections is a rotation different from R0, we must have, or we can write like this: H must have a rotation different from R0. Now in this situation we can use an exercise from chapter 3, the previous chapter. So by exercise 25 of chapter 3, that exercise says that in a dihedral group, either a subgroup has only rotations in it, or exactly half of the elements in the subgroup are rotations and half are reflections. So here all the elements are not rotations because H is not contained in this, and of course all the all the elements are not reflections that we have seen here. So that's why H will be of this form. And further, combining all these things with the fact that H has only 4 elements, so H will be of this form: R0, then R, F1, F2, where R is a rotation different from R0 and R distinct reflections. Okay. Now R is a rotation different from R naught. That means R belongs to this and R is a non-identity element. R belongs to this cyclic subgroup. And so R will be some integral power of this generator, and in fact because R is not equal to the identity, so K should be greater than 0 for some integer we can write 1. Using this relation and the formula for the order of R in terms of the order of R360 by n, we can now write something. Thus the order of R is equal to this divided by now we know that this order is n because that's how the group of all rotations has order n. N divided by GCD of n comma k. Okay, so we have found the order of this. However, from the structure of this group, what do we see? H has order 4. So H is an abelian group. Any group of order 4 is abelian. And F1, F2, because F1 and F2 are distinct rotations, so their product, distinct reflections, so their product should be a rotation different from R naught. So that means this must be equal to R. So if we now calculate r square, then the fact that h is abelian allows us to write f1 square, f2 square, but these two are identity, so this is equal to r naught. This combined with the fact that r is different from r naught tells us that the order of r is equal to 2. Okay, the order of r is equal to, yes, yeah, now we have got the solution. Now since f1 f2 is a rotation different from r naught, we have f1 f2 equal to r. Since h is of order 4, h is abelian. Thus, f1 square f2 square is r naught, which implies hence from this last equation n equal to order of r, which is 2 times GCD of this. And this last equation tells us that n is an even integer. It is, however, given that n is odd, so that is a contradiction. This contradicts the hypothesis that n is odd. So our supposition is wrong. That is, Dn has no subgroup of order 4, not cyclic, not non-cyclic. Then exercise 79. If n is greater than or equal to 4 and is even, okay, this time n is even, I need ink. And is even, show that the dihedral group Dn has exactly n divided by 2 non-cyclic groups. Okay. Of order 4. Okay, so now n is at least 4 and is given to be even. We have to prove that the dihedral group Dn has exactly n divided by 2 non-cyclic groups of order 4. So we start off by giving a collection of n by 2 number of non-cyclic groups of order 4, non-cyclic subgroups of order 4, and then we will show that there are no more. Note that Dn has the following n divided by 2 non-cyclic subgroups of order 4 whose elements look like this: R0, then R180, F, and R180F. Note that the rotation R180 exists in the group Dn because n is even, and F is of course some rotation, reflection. Why do I keep saying rotation? And how are we getting n divided by 2 non-cyclic groups? Because there are n divided by 2 choices for the reflection F. So we will get distinct non-cyclic groups of order 4. Order 4 we can see from here. Why is it non-cyclic? It's because if you see, in fact these are the things we considered in the previous solution also. Here these are two reflections. F is a reflection and this is a product of the rotation R180 and the reflection F, so it's also a reflection. And this is a non-trivial rotation. So orders of these two elements are 2, both of them have order 2, and this one also has order 2, just like that R had order 2 previously, same thing. So there is no element of order 4, so it cannot be a cyclic group because it will lack a generator. And by that same exercise 25 of chapter 3, these are the only non-cyclic subgroups of Dn of order 4. Exactly how we are concluding this from this exercise, that I leave to you to figure out. If you want, you can write here within brackets, note that R180 belongs to Dn because n is even. Otherwise R180 is not an element of Dn. We have already seen these things before. Okay, so this is the solution. And then if n, again n is greater than or equal to 4 and n is divisible by 2, but not by 4. Prove that the dihedral group Dn has exactly n divided by 2 subgroups of order 4. The number of subgroups of order 4 itself is n by 2. Since n greater than or equal to 4 is even by the previous exercise, Dn has exactly n divided by 2 non-cyclic subgroups of order 4. But at the same time 4 does not divide n. Okay, since four does not divide n, from the solution to what was that numbers, this 78, from the solution to exercise 78, which asks us to prove that when Dn has no subgroup of order 4, yeah, that one, since 4 does not divide n, 78, we conclude that Dn has no cyclic subgroup of order 4. But one thing is a little peculiar. No, this is not 78, sorry, this is 77. Yeah, that's what I was thinking. Determine the number of cyclic subgroups of order 4 in Dn, and there we have proved that the number is 1 if n is divisible by 4, otherwise the number is 0. So this is that otherwise case. So we will not have any cyclic subgroup in Dn of order 4, but non-cyclic subgroups of order 4 are there, and their number is n by 2. So the number of subgroups in Dn of order 4 itself is n by 2. Hence Dn has exactly n by 2 subgroups of order 4. This completes the solution. The remaining exercises in this set of exercises will be solved in the next group theory video from Gallian, and in the next video we will also start the exercises on permutation groups, that is chapter 5, I think. So that will be all for today, and the next video is, today is, what is the date today? 12, 13, 14, 15. And it will be on, here in this video we will solve ring theory exercises from Gallian, and then things will continue like this. So let me end things here. If you want to comment on these things, you can write in the comment section below, or you can mail me at my usual address. So see you next time. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.